Welcome to This Explainer. Okay, today we are taking a really fascinating journey through the history of computer science, but we're going to view it through a very specific lens, one that any organizational leader is going to instantly recognize. We're looking at the evolution from toxic micromanagement all the way to ultimate autonomous delegation. We'll explore exactly how systems architecture solved the absolute ultimate efficiency bottleneck and in the process, freed up the most expensive, powerful asset in the entire system to just do what it does best. Let's dive in.
All right, part one, the speed mismatch bottleneck. Now, the core problem here is this massive discrepancy, a fundamental hardware mismatch. On one side, we've got the central processing unit, the CPU, right? Operating at literally lightning-fast electronic speeds. It is the absolute powerhouse of the whole system. But on the other side, we have external peripheral devices, things like keyboards, mice, and printers, and these function at drastically slower human or mechanical speeds. If these external devices connected directly to the system bus, well, the incredibly powerful, super expensive CPU would hit a severe bottleneck. It would waste all its precious processing cycles doing absolutely nothing but waiting around for those slow components to catch up, and we definitely don't want that.
So, to prevent this massive inefficiency, modern computer systems introduce a really crucial component, the I/O module. You can think of this as an essential, intelligent middleman. It basically bridges that huge communication gap between the CPU, or memory, and the external hardware. You see, the operating system's ultimate goal is to manage these modules effectively to totally maximize CPU utilization. The whole point is to keep the processor 100% dedicated to executing useful computing tasks rather than just standing around waiting.
Brings us to part two, micromanaging or programmed I/O.
In this early architectural era, the CPU maintains absolute direct control over the entire data transfer from start to finish. When a program requests an I/O operation, the CPU issues a command to the I/O module and then it just waits. It enters this highly inefficient state known as busy waiting or pulling. It's literally trapped in an endless, repetitive software loop continuously checking the status register of the I/O module to see if the device has finished its task. And because the data has to flow byte by byte through the CPU registers before it can even reach the main memory, the CPU can't perform any background operations whatsoever. Zero multitasking.
So, that leads to our next breakthrough. Part three, the alert system, known as interrupts. Under this new technique, interrupt-driven I/O, the CPU finally stops wasting time hovering over the I/O module. Instead, it issues the read or write command and immediately switches over to other valuable system tasks. The I/O module just works independently in the background. Then, once that external device is actually ready to transmit data, the module sends a hardware alert across the system lines. This is the interrupt signal. When the CPU gets the signal, it pauses its current execution, saves its state, and automatically runs a specialized piece of code called the interrupt service routine to quickly grab the data. Once that's done, it just resumes its original work right where it left off. Now, while this completely eliminates the need for the CPU to just wait idly, it still has a pretty glaring limitation. The data itself must still flow through the CPU registers byte by byte. Going back to our analogy, it's like the CEO isn't waiting in the mailroom anymore, but they still have to personally stamp every single letter once they're told the mail has arrived. When you're trying to transfer massive modern files, think heavy graphics or huge databases, this byte-by-byte involvement creates immense processing overhead.
All right, let's fix that. Part 4. True delegation with DMA. Direct Memory Access, or DMA, is a real game changer. It introduces a dedicated hardware component that completely strips the burden of data movement right away from the CPU. This is the moment the CPU finally becomes a true high-level manager. Here's how it works. First, when a large block of data needs to move, the CPU configures the DMA module by sending it some parameters: the command, the device address, the starting RAM address, and the file size. Second, once it's configured, the DMA module opens a direct hardware shortcut, transferring the entire block of data straight between the peripheral and the RAM, totally bypassing the CPU registers. And third, the CPU is only bothered one last time when the DMA module issues a single solitary interrupt at the very end to say, hey, the job is done.
Moving on to Part 5, Autonomous I/O Processors.
This is where advanced systems moved way past simple automated modules and into completely autonomous units, known as I/O channels and I/O processors. We're not just talking about dumb pathways here. These are essentially specialized microcomputers embedded right onto the motherboard. They come fully equipped with their own local memory and independent instruction sets. So now, the main CPU simply executes a tiny little program, tells the I/O channel to take over, and washes his hands of the whole thing. The channel independently manages multiple complex peripherals, sorts data packets, controls subsystems, and, get this, even handles its own errors entirely autonomously. The CPU is effectively spun off an entirely independent division just to handle logistics.
Which brings us to our final destination, Part 6, the fully liberated CPU.
Let's take a quick look at this summary to really cement the journey we just took. Back in the era of programmed I/O, the CPU was a trapped micromanager, just massive waste. With interrupts, it became an alerted worker, much better, but still suffering from high overhead. Then came DMA, where the CPU stepped up as a high-level manager, giving us a massive performance boost. And finally, with autonomous I/O, the CPU is fully liberated, delivering nothing but pure computational performance. By historically delegating labor to smarter, more independent components, the whole system finally achieved its ultimate potential.